numbers. There really is a serious misconception floating around that basically pervades all of modern number theory. So almost all of these fancy modern theorems are in fact limited in extent. They need to be recast in a more limited, careful way. The bounds of possible applicability of these theorems needs to be investigated. Blanket statements are fraught with difficulty. So another serious problem is induction, where we try to prove things by this process of starting with one and then proving things one at a time. So this whole enterprise becomes problematic if we can't actually get to the numbers that we're interested in, say like Z again, by counting from 1 to Z, one step at a time. Really, if your proof that something is true for Z involves starting with 1 and then proceeding one step at a time, from 1 to 2, from 2 to 3, from 3 to 4, and then keep going until you finally get to Z. That's your proof technique. And then you find out that, in fact, wait a minute, most of the numbers that we encounter between 1 and Z are, in fact, not actually reachable. We can't actually get to them because they're so vast, not fit into the universe. Then that clearly breaks down the logical argument, right? That we no longer have proven our fact for Z. We've proven it only to the extent that we've been able to go from 1 to whatever number we're considering, one step at a time. It's a logical necessity. That if you only go one step at a time, you can only make statements about things that you get to by going one step at a time. So we need to reconsider a lot of things in number theory. We need to think much more carefully and clearly. We need to take into consideration the real dichotomy between small, comfortable, familiar arithmetic and this much more problematic, almost inaccessible arithmetic that we eventually get to when we start to explore far outside our comfort zone. And one way to start to try to make things more precise and to nail things down more clearly is to go back to the very fundamental questions that we started with this video with, which is, what is exactly a natural number? So sort of at the heart of the matter. What is a natural number? Well, we met at least 3 kind of tiers, identifiably different ways of looking at natural numbers. So our first tier is really the one that we started this series with, where we were thinking about natural numbers in a very primitive fashion, basically as a sequence of strokes or marks on a page. And that's sufficient for us to define arithmetic, multiplication, and multiplication in a relatively simple kind of naive way, where we in fact don't actually even need to have names for such things. We can say this is mark, 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 times mark, 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 equals mark, 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 mark. And a little bit of departure from what I did in that very first video is that now I'm putting these collections of strokes and marks in a boxes, because we're familiar with multi-sets. So we're using multi-set kind of idea here. This is a multi-set of marks. Okay, that sort of makes it a little bit tighter. And of course, we can then sort of recast this in terms of our familiar Hindu-Arabic formulation. This is really 7 plus 4 equals 11. This is really 3 times 4 equals 12. But then we can sort of represent this as just being a shorthand for this. So this kind of statement, from this point of view, is just a replacement or a convenient notation for expressing this more fundamental manifestation of the arithmetic of natural numbers. So with this view, a natural number is really it's a bunch of strokes and marks on a page, perhaps enclosed in some kind of box or container or multi-set. And then another big step up is to go to the Hindu-Arabic natural number presentation that we're familiar with, that we actually use in everyday life, where numbers now are things like 34 or 152. And the arithmetic is not at this level that we learned in primary school. 34 plus 152 is 186, 57 times 14 is 798, and so on. And although there's a natural connection between these two things, there's also a natural separation. And there's some senses in which this is a more sophisticated and more wide-ranging approach to numbers than this one. And then another big step is to consider just arithmetical expressions. So, for example, we could say, look at this number here, 3 to the 5th minus 14 squared. And that's an arithmetical expression for a number. And here's another arithmetical expression, 6 factorial. And here's another arithmetical expression, 13 times 59. Okay, so here we're working with some kind of arithmetical expressions, and we can do arithmetic with these arithmetical expressions as evidenced here. But you can see that this is going to be much more challenging to set up, because we have to decide, well, what kinds of expressions we're going to allow, what are the rules that we're going to adopt, when are we going to decide when two expressions are equal, and so on. So, although we could, and perhaps we'll talk about this, it might be useful for us to really separate what we currently have. So currently we jumble all these together and say, oh, consider this number here, that's 4, and consider this number 798, and consider this number 13 times 59. We treat them all as more or less just different manifestations of the same thing. But what I'm saying here is that what we've been talking about really leads us to want to separate things into different levels so that there are different kinds of natural numbers. And we might actually introduce different types for what currently is just only one type. So we could say reserve nat to be a primitive natural number of this kind. And we could use num to represent a Hindu-Arabic natural number. And we could introduce something like num expression or num x to denote some kind of arithmetical expression. Although we have to be more precise about the nature of this kind of object. So this way we would have different levels of natural numbers and not just a single all-embracing container that we currently have. So let's say a little bit about that first type, the primitive natural numbers. So note that we're going to use MSets or multisets as containers for that. So that we really are adopting this data structure point of view here. And it's another example of a very useful application of multisets, that they give us a vehicle for introducing and creating the natural numbers. Okay, so this is very different from the set theoretical formulation, as we described a few videos ago, attributing it to John von Neumann, the idea that a natural number is a set of sets, and everything is built up from the empty set, in terms of sets, empty sets, and other sets, and so on, so it's nested inside each other in a rather complicated way. So here the possibility is that we can simplify things dramatically because we can use the M-set notation, then we only have these single primitive objects, which we might call a stroke or a mark, which then going to populate our source. So here is a definition. Okay. A definition of what a natural number is. Actually more precisely, what a primitive natural number is. We want to be a little bit more specific. So a primitive natural number is an M-set of marks. This is what we call a mark. An M-set of marks is a natural number, and this type, nat, is going to be now our type that represents a primitive natural number. So an M-set of marks is specified by writing it down clearly and completely. There's now only one way of really officially writing down a primitive natural number, which is to write it out like this. It's an M-set of marks, so you have to make all the marks, and you put them in a square bracket box, and that is a natural number. That more precisely is a primitive natural number, an element of that. So note that this is similar, but somewhat different from our very first lecture, MF1. In that lecture, we hadn't talked about data structures. We didn't have the idea of sets, or lists, or multisets, or multisets, and we didn't put our strings of marks or strokes in a box or container. But now that we are familiar with multisets and we're a little bit comfortable with them and we recognize that they're flexible objects, we are going to do that. So we're going to shift gears just a little bit. We're allowed to do that. And we're going to now regard a natural number as a M-set of marks in the usual M-set notation. So M-sets, of course, I remind you, allow repetition. We definitely need that because there's only one type of thing that's happening here. And there's no commas because the order doesn't matter. If you interchange the order, it doesn't matter. It doesn't change things. Okay, so this is really a fundamentally new but simple approach to really fundamental objects in mathematics, natural numbers. Now we're going to think about natural numbers. Okay, and it's well worth pondering about the pros and cons of this proposed definition. So let me reiterate that again because it's rather important. So in natural basis 1, we did define a natural number as a string of ones, and we expressed this natural number as 1, 1, 1, 1. So we consider the stroke as being 1. Okay, so here we're departing from that. So our basic object is this stroke or mark, which is not to be identified with the number 1, which is rather this. So the number 1 is the M-set consisting of a single mark. Here I've written it again. Okay, so this mark here is not the number 1. The number 1 is now the M-set consisting of that single mark. That's the number 1. So this is a departure from what we did before, utilizing our familiarity with M-sets. There's some clear advantages in making our natural numbers as multisets of these strokes or marks. So in particular, the boundaries are clear. So there's less ambiguity or possible confusion when we have lots of different natural numbers sort of on the same page or on the same line. If we don't have the boundaries, then there's more likelihood that these things will run together, especially if we're wanting to juxtapose them or get them close to each other. So in particular, if we're multiplying M-sets, say like this, then it's completely clear what we're doing, and we can get rid of the multiplication sign and just juxtapose the two M-sets. So that's now possible. But if you didn't have M-sets there, then this would be a rather dangerous thing to do because you'd be easy to confuse this one with what we call 7. And there's another interesting consequence of working with M-sets, because we've seen from our experience that in the world of M-sets, there is a distinguished M-set, which is the empty M-set. Okay, so this empty M-set, which we denote like this, is both natural and useful. And so if we're going to define a primitive natural number as an M-set of marks, then it follows that we should allow the possibility of having an empty M-set of marks. And so that means that what we usually thinking of 0 naturally plays a role here. It naturally arises as a type of natural number, which is of course different from the historical story. It's also different from what we did in the first part of this series. We have up to now not treated 0 as a natural number. But now we see that when we make this shift to this data structure point of view, regard natural numbers as M-sets of these more fundamental marks or strokes, then it's natural to allow 0 in the picture, and so 0 becomes a natural number. So this is a shift that we're making. And I don't apologize for it. I think we're open to the possibility of changing our minds. It's very important to have this ability and this willingness to change our minds. Let's do things a little bit differently from the way we thought we were going to do things before. Right? This is mathematics. It's not set in stone. We can proceed, erase something, change things, reconsider, look at things a few years later and say, actually, we should have done this, this, and this. And we need to be prepared to then go back and actually do things the better way, to rub out what we've got and to write in a new and better way. That, of course, applies to a lot of modern mathematics. And of course, the computer scientists can now rejoice because now 0 is part of the natural number system, which computer scientists enjoy because that's starting to count from 0. So this is very exciting. So we've harnessed our understanding of data structures for something very concrete and actually fundamental. Namely, we are pinning arithmetic onto the multi-set framework. We are creating natural numbers from a relatively simple kind of ingredient, and with this very important data structure kind of thing in mind of a multi-set. In our next video, we want to do something that's even more fundamental. We want to go down right to the bottom of the core of mathematics. So the natural numbers are pretty close to being at the core of mathematics, but I claim that there's really something underneath the natural numbers. That's sort of implicit in what we've been talking about here, but I want to really identify what it is. So this is a fundamental dichotomy in mathematics, a kind of a yin-yang, which hasn't properly been identified. We need to put our fingers very clearly on this and really identify this fundamental dichotomy which is at the core of mathematics, and that we are going to use to build up our arithmetic in I think, a beautiful way. So in our next video, it's going to be a rather important one in the sense that we're going to really introduce a almost philosophically novel way of thinking about what mathematics ultimately is really about. Once we get right to the bottom, that's the essence of mathematics. We're going to find out next time. I hope you're sorry for that. I'm Nolan Wapner. Thanks for listening. Today, I'm Nolan Wapner. Today we want to go really far out in this remarkable successor limit hierarchy that we outlined in our last few videos. So basically what we're doing is we're creating bigger and bigger arithmetic by thinking about sequence of operations, extending addition and then multiplication and then exponentiation, and then this triangle operation that we've used quite a lot, the square operation and so on. We want to extend this list of operations in a rather interesting way. Basically relying on two ingredients, the idea of the successor of an operation and the idea of having a limit of a given sequence of operations. So if we have a suitable sequence of operators or operations, say cross 1, cross 2, cross 3, then we can concoct this limiting sequence. So with these two different ways of extending further, we want to now explore the possibilities. And one kind of underlying question here is, how do we actually get our heads around what precisely a suitable sequence is? There's a bit of an open-ended aspect here that we want to explore, so we're going to try to pin things down, but I'm not going to pretend that I have a fully-blown, completely laid-out theory here. In fact, one of the interesting aspects of this whole story is that it may not be possible to lay out from the beginning what we're going to do. It may be more like you proceed in a certain direction, and then once you get to a certain level, you have to start making new decisions. And the new decisions that you have to make aren't, at least initially, apparent from where you began with. So it's kind of the zigzagging element that really requires you to think in a novel way, continuously or sequentially as you proceed. All right, so I do hope that you've had a look at the previous videos because we haven't. This is going to make a lot of sense. So make sure you've watched the last few videos. And there we've created some kind of hierarchy, starting with these relatively simple operations that we're familiar with, and then proceeding on. Okay, so we started with the operation of addition, and then these star operations of multiplication, and exponentiation, and the triangle operation. Star 1, star 2, star 3. After that, something that's a limit operation, which we call star infinity, and then shortly star n. Successor of star n is star n plus 1, successor of star n plus n is successor of star n plus 1, and then we have triple of successors. Star 2 is 2 to the raised star 2n, and 6 more successors to the raised star 3n,
现在我知道能够一天买回自然果的豆子。
Limits, and then we have level 1 limits, and then we have level 2 limits, and then eventually we get from that a level n limit. That's occurring right here, that's our first level n limit. In some sense, that's a reflection in the red arena of exactly this first initial sequence in the black arena. Here's 1, 2, 3, with limit n. That's being reflected in having 1s, and then 2s, and then 3s, and having limit n. And then what happens is, again, a kind of repeat of what we had before. So there's a kind of a self-similarity that starts to appear here, that the sequence of red numbers, which records the level of the limit, starts to look a lot like the original sequence. So as it says here, we've gotten up to n plus 1. So that's just up to there, right? We made the transition, we've gone, in terms of the red label, we've gone all the way up here, and now we're at that stage there. So we would expect that, as we keep going, the red labels themselves are going to start navigating through the same table. We have self-similarity here on the fractal aspect of something.